Hello everyone, and welcome back to Nailing Your Thesis, our course on how to perform research. In the last few segments we talked about the overall research process, what constitutes a good research question, and what is and how to find relevant and related work in order to put your research work into context. Today, or in this segment, we will be talking about contributions. Now, that's another funny term that scientists are using with a specific meaning, and contribution means a publishable research result. It's a shorthand basically for your contribution to the progress of the state of the art, the new insights you generated. And like paper is being used in a special sense, contribution is also being used in the special sense of a research contribution in the language of science. It's so important that you understand your contribution because it's what makes your work publishable, that scientists, authors of research papers, have decided to break it out explicitly in the form of a bullet list in the beginning, in the introduction section of papers these days, so that reviewers do not miss what is new and novel and interesting about your research work. So literally in modern research papers you will find some paragraphs starting with the words, the contributions of this paper are the following, followed by a bullet list, an overview list of what you believe your contributions to the progress of the state of the art are. Now, the actual description of the contributions in detail to make a reviewer and reader believe you actually achieved progress, that comes later. That comes after related work, etc. But here it's upfront to not be missed and detailed later on. So here's a cartoon. Sometimes I wonder whether if there's more to life than unlocking the mysteries of the universe. Well, the answer to that somewhat humorous question is of course left to you and your priorities in life. In general, as we perform research, we have a fairly simple setup, certainly on the level of final theses or single research papers, because usually there is a hopefully well-defined research question and that already leans towards a particular research method to be applied to answer that question. And so the structure of that research work is fairly linear. There's a question, there's an obvious method to apply, you apply the method which gives you data that you interpret properly in order to answer that research question. Now, in other contexts, for example, in larger contexts like a dissertation, or even larger contexts like over a research project, a principal investigator may have to break down a big research question into its bits and pieces. And then there needs to be a logical connection between these bits and pieces in order to answer the big research question as a whole. So even though you probably won't have a complex research argument which answers these research questions to make in your final thesis, it's good to understand what to do if you have a big research question, a large research question that can only be answered by working through multiple smaller questions, answering those and putting the pieces together into a larger whole. And that is done by way of a research argument. So in this segment, or in the next few slides, I want to discuss what makes up good scientific argumentation so that you can recognize if you're looking at one or may not be looking at one. A research argument is, of course, what you use to answer a research question. If it's really small, it's just the application of one method. If it's large, it is that theory that you support by your research argument. For example, by breaking down the theory in many propositions or hypotheses it makes, and then showing how, as you evaluate these hypotheses, the theory may likely be true. We had an example. Actually, it was on the level of a single paper, so we needed a research argument to show that open source is here to stay. And we broke it down into these bits and pieces, actually two pieces, two separate hypotheses, which were open source is alive and open source will stay alive. And so here we have now one general conclusion based on two smaller insights or hypotheses that were validated as part of this research. The general structure looks like this as you try to make a research argument. You have that final conclusion, that answer, that theory to your research at the top, and you break it down into these hypotheses and supporting arguments that all aggregate and fuel or fill in, lead to that top level conclusion. This illustration here is for illustration purposes only. Typically, it's a much broader hierarchy where lower nodes in the hierarchy support the higher up ones. Again, at the top is the final conclusion or that theory you want to have, want to provide as an answer to your question. So the structure of this particular hierarchy is always the same. Every node in the hierarchy represents a hypothesis. It's supported by those lower, and what we will look at is the logical relationship between those nodes on one level and how they support the higher level node, the higher level conclusion to be made. The benefits of this approach is, if you do it right, is strictly or clearly divide and conquer. You break up something complex, something that's hard to answer as a whole into bits and pieces. And if that reductionism can actually work out, you do get a nicely structured argument that makes it believable that your main conclusion is true as well. It's not only divide and conquer, sometimes it's the only approach really to something messy and complicated. It's commonly seen then in science, at least for larger pieces of work, to the extent that people literally have a numbering scheme as they present to a reader. The structure of their research arguments with, say, a research question at the top, supporting hypotheses, if evaluated to true, they would be supporting, broken down into these levels of the hierarchy. And you can see how there's a numbering scheme associated, H1 for hypothesis 1, H2 for hypothesis 2, 1.1 for one level down, 1.2 for a level down, etc. While the illustrations may suggest it's a deep and narrow hierarchy, in reality actually it is not very narrow, but rather quite broad, meaning there are lots of hypotheses supporting one research question. In fact, if you read research papers, if they do take this approach, they will have one big research question and then just one linear list of hypotheses, say 1 to 10, and not much further down the tree. Here's the alternative numbering scheme. If the research question really is just one big hypothesis itself, then you'd simply move up the numbering scheme by 1 in this hierarchy. Even though there's only one primary hypothesis, H1, that's what you call it. I think this mathematician says to the other, reviewing his work in this case, I think you should be more explicit in step 2. Step 2 is obviously where either the original author on this chalkboard or maybe simply the cartoon is put down then a miracle occurs. Oh well. So there is something missing. The missing link in this proof probably being suggested. And of course, any proof, any research is only as strong as its weakest link. It's all interacting, and the overall strength really is determined by the weakest link in the argument you're making. So we will look at the basic forms of reasoning. While you might think these are this calculus-based reasoning, this is actually pragmatic in the sense that we do not assume a closed world here where there could be perfect deductive reasoning. As we will see, there is no such thing, at least in an open world, but from a pragmatic perspective of a theory being only as good until the next better one comes along, this is pragmatically convincing and sufficient for science. Anyway, I'm jumping ahead. So I want to look at 3 types of reasoning that help you build a research argument hierarchy and what it means. So inductive reasoning is quite simple. By looking at observations that all seem to conform to support one primary hypothesis or one answer to a research question or theory, you keep piling on, and it becomes more and more believable by not finding that exception that your primary conclusion is probably true. And your inductive argument will be even stronger if you can show that these 4 supporting or n supporting arguments are actually covering the whole space. And that's actually what we did in the open source example. We looked at 2 time frames, that open source is alive today, that's important, and that it will be alive in the future. And then we covered all of time with these 2 simple time frames, and hence it's believable that the conclusion works for is and will stay alive. There's a nice term for it, MIC, mutually exclusive, completely exhaustive, which you should have in your inductive reasoning as you look at the supporting arguments. Ideally, they don't overlap, they are orthogonal, they are mutually exclusive. And also, when put next to each other, they completely exhaust the space. Then, if you have MIC properties, you have a good argument, a believable argument that the conclusion is true. In reality, of course, you may wonder, will I ever be able to exhaust the overall space? In reality, meaning an open world? Of course not. But it's always the pragmatic assumption that everything else somehow has been taken care of, for example, by random variation in all possible other variables, which usually leads to this key statement, ceteris paribus, all other things being equal. If you have no reason to believe that there are any hidden variables, you will argue that, but of course you will only be believed as long as no other hidden variables are being discovered. But again, science progresses and theories always have a time limit on them until the next better one comes along. So the second type of reasoning of relevance to a good research argument is deductive reasoning, where you build on steps and in a sequence of logical steps you come to a conclusion. So you don't put things independently next to each other as an inductive reasoning, but rather you make a strict or strong, somewhat calculus-based argument, and that supports your final conclusion. Here's the classic example that you may know from philosophy or logic, and you have a major assumption, a major premise, all men are mortal, a minor premise, Socrates is a man, so you can conclude Socrates is mortal. This is something you can apply in a research argument. If you can show your two premises are true, then your conclusion will also be true. So you set up the hypotheses as a major and minor, or several of those premises, and if they come together, the logic of the domain will dictate that the conclusion, the higher level hypothesis, is true as well. Again, this calculus-based reasoning would be correct in a closed world, but the real world is not closed, it's open. There are always unknown variables, so there are obviously limits to deductive reasoning, but again, it will be considered true until the next better theory comes along. Finally, there's something called abductive reasoning, which is really not a reasoning at all, but let's say a plausibility or a probability argument where the observation's premise implies a probable conclusion. So if you know that, if you observe that Socrates is mortal, and you know that all men are mortal, you may conclude that Socrates is a man. Well, unless you realize that maybe Socrates was the name of your cat. Here there is no strict deductive logic, but a probability, but you may also be wrong. Still, because in the real world we are dealing with probabilities, you could make this argument knowing well that there might be alternative explanations out there, but still use it and argue its cause. Still, of course, people will quickly point out the limits of this abductive argument to you, hence we are not overusing it. Okay, so for any contribution, you will have to conform to quality standards. It's one way of assessing your research work. These quality standards are actually tied typically to the methods that let you come up with a conclusion, like a validated hypothesis, a validated premise, something like that. And so they are tied to the particular method. We will look at these quality criteria then in the context of the respective methods. Let me just say that the classic empirical quality criteria are construct validity, internal validity, and external validity, as well as reliability, and what that is we will discuss in the lectures on controlled experiments and related. In qualitative exploratory research, maintaining these or achieving these qualities is hard. Hence, there are some alternative models for evaluating the quality of exploratory research, but we will also go into those only in the respective lecture. So here's a link from the slides for working with data, and let me conclude with a short summary. So we looked at what this funny term contribution means in science, and then we looked at how your contribution is logically, you can logically substantiate it by way of research arguments, and then, if you will, archetypal forms that these research arguments can take as they form a hierarchy, how one node in the hierarchy is supported by the lower nodes in the forms of either inductive or deductive reasoning, possibly working with probabilities, also with abductive reasoning. And always to be reminded that these calculus-based type of thinking may well work within a closed world, under a closed world assumption, but that we are researching the open world in which there will always be well-known variables, which implies that your conclusions and the supported theory will only be as good as the next theory that will come around and will be better by improving over your work. That's it from me. Next up is ethics and research, which will conclude our overview set of segments, after which we will go into the different research methods, confirmatory as well as exploratory research methods that you might be working with in your research project. Thank you and see you then. Bye.